Good morning. In lecture, I had screwed up the recording of the first slide. I just had a few announcements before we get into today's lecture. The announcements were to look for an announcement from Sophie White on setting up your iPad for Lockdown Browser. Lockdown Browser is going to be needed for next week's midterm. Just remember, we have a midterm next Wednesday night. If you have a schedule conflict, look for the exam attendance policy in Carmen, fill out a request for an alternate time exam if so. Be ready to take the exam, obviously, as we're approaching the midterm. Think about doing lots of practice that gives you good practice with authentically solving problems using your own knowledge and problem-solving abilities. So daily quizzes, practice midterms, etc. There are 3 practice midterms that have posted. Those are cumulative exams from chapters 1 through 3. I would get through your studying of chapter 3 before looking at those exams. Take them like the real exam. Those actually were past midterms that were used. You can use those to gauge how well you might do in the real midterm and to help you figure out what materials to study in your final preparations for the exam. All right, so we'll get into the lecture. Okay, so we were looking at the problem last time of how many chlorine molecules there were, how many chlorine atoms there were within a 3-gram sample. So we looked at this problem last time in lecture. And we were using the conversion of molar mass to go from grams to moles. We were using Avogadro's number to go to the formula unit. So an Avogadro's number of formulas are in a mole of the formula. And then we were using the count that each chlorine molecule, so each Cl2 molecule has 2 chlorine atoms to go to the chlorine atom for the last part of the problem. So if we look at the next problem here, what's the mass of a certain count of molecules of methane? So we can go through this problem here. In fact, I'm going to calculate the number of moles. So I might ask, what is the number of moles in the sample? So the moles of CH4 that are present, because we're going to go through that step first, and then from there we're going to go into the mass. And so we can maybe look at this problem in 2 steps. And so I want to make sure that we're kind of clear on the different sort of pieces of information we have about problems like this from Avogadro's number and also just from the periodic table. So we can use the periodic table to calculate that the molar mass of CH4 would be 12.01 for the carbon plus 4 times 1.008 for the hydrogen. So that's going to be 16.04. Now that's either AMU per molecule or we saw 16.04 grams per mole. So we can get the molar mass from the periodic table, or we can get the atomic or the molecular weight of CH4 in AMU per molecule. So in a lot of problems, I think the grams per mole will probably be the unit we use the most, but we could also, in some problems, use the AMU per molecule conversion factor or molecular weight that we could get equally as well from the periodic table. We can also look at the formula and see that we have, for every 1 carbon, we have 4 hydrogens. So 1 CH4 molecule would contain 1 carbon atom in a ratio to 4 hydrogen atoms. So we could also write for every 1 CH4 molecule that it contains 4 H atoms. So we see the connection between an individual atom and the molecule. So we can look at the ratio of molecules of CH4, so 1 distinct molecule of CH4, 1 carbon atom, 4 hydrogen atoms. And so this is just from the formula. And then from Avogadro's number, which we usually symbolize as capital N, lowercase capital A, but from Avogadro's number, we would have that there's, in 1 mole of CH4, that would be equal to or contain 6.022 times 10 to the 23 CH4 molecules. So in a mole of CH4, we contain that Avogadro's number, 6.022 times 10 to the 23 CH4 molecules. Just think, so 1 mole of X, whatever X is, you get a mole of whatever X was. So you can have a mole, in a different context, you can have a mole of hydrogen atoms. You can have a mole of H2 molecules. You can have a mole of CH4. And in each of those cases, you either have a mole of the H atom, a mole of the H2 molecule, or a mole of the CH4 molecules. And so these are the conversion factors we can use in this problem here. So if we're trying to calculate the number of moles of CH4 first from the number of molecules, I mentioned I like to use mol(C) for molecules for the symbol. So I have this many molecules of CH4. If I'm going to moles, that's just Avogadro's number. So the conversion to go to moles would just be for every 6.022 times 10 to the 23 molecules of CH4, that represents 1 mole of CH4. So if we just divide this quantity by Avogadro's number, I get 0.0332 moles. And then from the number of moles of CH4, I'll just write from this number of moles of CH4. If we want the mass of the sample, we just use the molar mass. So we just be using that we have 16.04 grams per mole of CH4. So from the number of moles, 0.0332, I'm just multiplying this by 16.04. So this is just the moles that we calculated over here. Multiply by 16.04, I get 0.533 grams. So we had less than a mole of CH4 present because we had less than 6 times 10 to the 23 molecules present. So we had about 0.0332 moles of CH4 present, and then that has a mass of about 0.5 grams, 0.533 grams. Okay, so that's how we can go from sort of grams to moles with the molar mass. We can go moles to molecules with Avogadro's number. Then we go to an atom count with the formula. Okay, let me throw this example to you guys here. I'm just taking, the MgNO32, so magnesium nitrate. How many nitrogen atoms would be present in a 4.72 gram sample of magnesium nitrate? Might take a couple minutes. I'll give you guys about 2 or 3 minutes to try to work through this one. Yes? We can think about so the conversions I would use here are like grams to moles from the periodic table, from the molar mass we can calculate, but it would be for every 1 MgNO32, and this example here would contain 2 nitrogen atoms just from inspection of the formula. So we're just looking at the formula, seeing I have 2 nitrogen atoms for every 1 unit of MgNO32. All right, let's talk about this one here. I still see probably a few of you guys are still working. But if you're getting the idea of the problem is just being able to go from grams to moles to units or molecules. This being an ionic compound is a little bit weird with the way we think about quote unquote molecules, but we'll talk about that in a second. And then going to N atoms in the process is our plan. So we start with our 4.72 grams of MgNO32. We have to use the periodic table to come up with the molar mass of 148.3 grams per mole of MgNO32. For every mole of MgNO32, I have an Avogadro's number of whatever that is. And so the MgNO32, we can think of that as either molecules was the CH4 example. So we could picture having, 1 mg, a nitrate here. So we have an Avogadro's number of the units of that ionic compound. So we'd either be writing molecules here or units. And units is probably the better word for an ionic compound since it doesn't really exist as that molecule. But you can think of it as a molecule. Like if you're picturing one distinct connection of a carbon to 4 hydrogens in the previous example, you could picture 1 magnesium, 2 nitrates as that unit, or if you want to call it a molecule, you'll still get the same answer. It just really isn't a molecule in the sense like a molecular compound is. Like in the sense that MgNO32 just never exists as one thing. It always exists as multiple ions connected together, where you can have one distinct water molecule with like an O and 2 hydrogens bonded. So molecular compounds exist as molecules. Ionic compounds comprise of the units of the compound. But you could think of it almost the same way that you think of like molecules. So very similar if you're picturing a molecule here. But then for every 1 MgNO32 unit or molecule that you're picturing, you have 2 nitrogen atoms because we have the 2 nitrogens and nitrate within one of the formulas of that compound. And so we do this math here. I come up with 3.83 times 10 to the 22. So the sample contains a lot of nitrogen atoms. Looks like answer C. Okay, so well, yeah, so why did I not carry one more digit here? I guess I just, I calculated, I had 148.32 as well on my calculator, and I just kind of rounded it to the 4 sig figs because I knew the mass had 3. So when I saw that this here has 3 sig figs, I just really need to carry at least 4 here, and I'm going to not have a different answer. So if I carry an extra decimal place, it wouldn't have changed this number placeholder here. Does that make sense? So there's nothing really wrong with using more sig figs. You just want to use enough sig figs. So I just made sure to use enough sig figs. I had one more than the limiting sig figs in the problem. And so like on a lab example, you want to be usually more precise than a lecture problem because usually your masses are known to a greater precision. Yes?
Whoever doing these calculations, we shouldn't worry too much about the sig figs as long as they're going out at least like 3 or 4 decimal places.
Well, I guess like the worry about sig figs part to me is I'm just looking at this as 3 sig figs, so any conversion factor I use should probably have at least 4, is my only kind of thought. Is if I'm using at least 4, in most lecture problems, we're not going to be too precise with masses, but I'm usually just trying to carry 1 extra placeholder. On a multiple choice test, I don't think you're ever going to get too tripped up if you happen to just use 3 sig figs and you round things a little bit shorter. You probably won't have much of a problem on a lecture problem. It's really more in the lab when you have like 5 or 6 units of precision. That's where we're like using 6.02214 times 10 to the 23 and getting those extra 2 digits and looking them up. Probably the next logical topic or the next logical thought would be how do you get formulas? Yes? Okay, so we actually did this problem previously, or thought about this before, where when we have these 2 compounds that, we have some molecular formula here that has the empirical formula, the simplest ratio of CH2O, that they had the same percent carbon. So we had worked this out previously, the percent carbon, and both of these worked out to be about 40.00%. And so we could go back to the last lecture slides and go through that if you want to see that again. But we calculated both of these, and the key is really seeing that for a molecular formula and its empirical formula, that they're going to have in common the exact same percent masses as each other. And what this is going to lead to, if we're using percent composition data, is that we should be able to get a formula from it, but it's going to be the empirical formula. So we're going to see that percent composition data can be used to find the empirical formula of a compound. And we mentioned before, the empirical formula doesn't really tell you much about the molecule. The molecular formula and the molecular structure are really what you want to know. So if you want to really know the molecular formula of a compound, you would do a two-step process. You would do some sort of an experiment that tells you the percent composition of each of the elements in the compound. Then you do a second experiment that tells you the molecular weight. If you knew the molecular weight in the empirical formula, you can figure out how many units of the empirical formula are there in the molecule. And so this is just kind of like a thought of how we're going to see some problems presented to on percent composition data. And so the percent mass of a pure substance can help lead to the empirical formula of a compound. And so we're going to see, we'll do an example in a minute of how if we know the percent CHO or whatever the elements are in the compound, we can use that data to get to the empirical formula. And then the molecular formula can be obtained from knowing the molecular weight and then dividing it by the empirical formula weight. We'll do an example of that in a minute. Okay, if I bump this stupid thing, it turns off. These stupid monitors in here are driving me bonkers, especially this middle one. Okay, mostly back in business. And so from a molecular weight empirical formula, knowing those two details should help us find the molecular formula. And then another type of problem will be presented to us where we can combust a compound into like CO2 and water. And from the mass of CO2 and water, we can actually go back and figure out some composition information about carbon and hydrogen and maybe some other elements within a sample. So a combustion analysis problem will be another type of problem that we look at for trying to establish formulas of compounds. Okay, so if we can determine an empirical formula, let's look at this example here. So we have the compound para-aminobenzoic acid. It's listed as PABA on like sunscreen. Has the composition 61.31% carbon, 5.14% nitrogen, or 5.14% hydrogen. Nitrogen is 10.21%, and oxygen is 23.33%. Can we find the empirical formula of this compound? Okay, and so these ratios here are all by mass. So these are all the mass composition data. And so if you know the composition of a compound by mass, we should be able to work those masses into a ratio of either the moles or the atoms in the sample. And then the question there becomes, can we come up with the simplest ratio of those moles or atoms to each other? So if you knew the ratio of the moles of the elements within a sample, you could then figure out the simplest ratio. And the simplest ratio would be the empirical formula. And so our goal here is going to be to take some ratio of masses for this compound that are given or are equal to the percent masses that are given. So often you see in these problems, you start with 61.33 grams of carbon, because we know that would be in ratio to 5.14 grams of hydrogen. That would also be in ratio to 10.21 grams of nitrogen, and also in ratio to the remaining mass, 23.33 grams of oxygen. So some problems say, assume the percentages are masses. Really, we just have to start with some ratio of the masses that's actually true for the sample from the information given in the problem. The easiest way to do that is to just use grams in place of the percentages. If you notice, all these percentages, in fact, I'm going to double check, these should all add up to 100%. Not the 100.01. So we're adding up to 100%. So 100% of the sample is represented by these four elements here. And so we're just using a ratio of these masses that we know to be true. If you know the ratio of the masses of each of these elements in the sample, can't we come up with the ratio of the moles very easily just by using the molar mass of carbon? So we just have to use the molar mass of each of the elements. So it's 1.008 grams per mole of hydrogen, nitrogen's 14.01, oxygen 16.00. Now, I could do one of two things here. I could stop and calculate, which you can see I'm going to do since I wrote a bunch of equal signs, or I could have went to atoms. I could use Avogadro's number and multiply all of these by Avogadro's number and go to the atom of each, so I can think of the ratio of the atoms. That might make sense, but it almost is an unnecessary step. If I need to multiply all these by some big number to go to the atom, and it's the same big number, Avogadro's number would be the same number for each of these moles to the atom of each, then I'm almost introducing a needless step. I can just stop at moles and try to calculate the ratio of moles within each of these, for each of these elements. Let's see if they'll just buy me a big iPad and just hold it up in the future. This is getting ridiculous. What the heck? Okay, well, if you were with me in converting each of these to moles, work on calculating the moles, you guys can do that too. And then let's try to think about how we can get a ratio. So think about how you're going to get the mole count. Think about how you might go from the moles of each that you get to the simple ratio. Think about how you maybe divide by the smallest number and start thinking about multiples. And hopefully we'll get a screen back up after we get some numbers written down. Okay, so I think hopefully you guys were able to get the idea that we're just going from grams to moles using the molar mass of each of the elements and the compound. But think about how we had the ratio of those moles. Like we start with a ratio of the masses. That's why we're kind of thinking of this mass to this mass to this mass to this mass as a ratio. So then I have a ratio of the moles. And so at this point, like I could maybe write a formula. This would be kind of silly, but you can maybe get the idea of what we'll do in the next step if you think of this process here, is that the formula would look like kind of C 5.1, N 5.1, nitrogen 0.73, oxygen 1.5 or something like that. Like that's not really a clean formula, right? That's not the simplest ratio of these elements. So what we need to maybe do is figure out, well, what are these ratios here? So let's erase these. And so how might I just mathematically figure out the simplest whole number ratio? It just becomes more or less a math problem of how do we most easily accomplish that task. I would probably identify the smallest one first, because I know if I divide all these by the smallest number, let me double check a number real quick. I think I might have wrote it down wrong. 10.21 divided by 14.01. I want to... divided by 14.01. Okay, for some reason I was thinking I wrote a different number down. Okay, so I'm dividing all these by 0.7288. Now I can do anything I want to these numbers so long as I do the same thing to each of them and I keep the ratio intact. Like I can't divide one by a different number than the other. So I can divide any of them, or excuse me, I can divide all of them by the same number, and I'm keeping the ratios intact. So I got to worry about all these ratios being intact. So that's why I have to divide all of them by the same number. And we're at least going to get one whole number if I choose the smallest. If I choose the biggest, I'm going to get all the others in fractions. That's not really going to help. So if I choose the smallest, I at least get one whole number out here. I'm going to get 1 mole of n in ratio to the others. And so if I do 5.107 divided by 0.7288, I get 7.001 if you're being careful. For hydrogen, I get 6.996. And for oxygen, looks like I'm going to get 2. I get 2.001. So then you might wonder, how close do you have to be to round to 7 or to round to 2? It's usually going to be within about 0.05 or less. It should be pretty dead on, as long as we wrote the question well. And so you're going to see that if you're within about plus or minus 0.03 or so, that you can round. So you can round to that nearest whole number. So that this is going to round to 7, this is going to round to 7, obviously 1 and a 2. So our simplest whole number ratio here is going to be C7, H7, and then NO2. Yes? Oh, yeah, I just transcribed that wrong. Yeah, thank you. So it should be 5.105. And that's going to be closer to 7.000. Okay. And so this would be the empirical formula. The simplest ratio of C to H to N to O in this compound. Now, this could be the molecular formula. We just have to know the molecular weight. So something you could calculate is you could say, well, what's the empirical formula weight? So there's just the 7 carbons. So 7 times 12.01 plus 7 times 1.008 plus the 1 nitrogen 14.01 plus 16.00 times 2. This is 137.13, call it 0.14 AMU. So that's the mass of this empirical formula. So now if we go to do an experiment to find the molecular weight, what we should find the molecular weight is either going to be about 137, or it should be about twice this, it should be about 3 times this, 4 times this. So we're going to have some multiple of this empirical formula in the molecular formula of the compound. And so that's what we're kind of, in a second experiment, if we could determine that the molecular weight of the compound is actually 137.1, then we're just taking our empirical formula weight, we're taking our molecular weight that we find for the compound. So take the molecular weight and divide it by the empirical formula weight. And this is going to give you the multiples of the empirical formula in the molecular formula. So the molecular weight 137. So this just being the molecular weight, MW. Empirical formula was 137.1 as well. So we have one multiple. So in this case here, we're going to have one multiple of that empirical formula. So 1 unit of the empirical formula. In the molecular formula. So the molecular formula would just be C7H7NO2. But see, we never would know this is the molecular formula without knowing the molecular weight. Like we can calculate the empirical formula weight and see it's 137.1. Then we have to do an experiment. We have to do some other, get some additional information to figure out what the molecular weight is. So it could have been 274.3, which case it would have been C14H14N2O4. So if instead the molecular weight was 274.2 or 274.3, then we'd have that mass divided by 137.14, and that would equal 2 units. And so the formula then would be C7 times 2, H7 times 2, N1 times 2, O2 times 2, for C14, H14, N2O4. So we have to keep the ratio of the formula, we have to keep that empirical formula ratio intact, otherwise we don't have the right empirical formula anymore. So whenever we're thinking of these percent mass problems into formula, we have to think about ratios of masses to ratios of moles, keep the ratio intact, figure out a way to divide by the smallest value, so divide all the moles by the same value, get your ratio, and then find that whole number ratio. So another example here would be like the CH2O, or the CH2O example. We kind of looked at this previously last lecture where we determined this empirical mass was about 30. So it's 12.01 plus 1.008 plus 16.00. So that's 30.03. And if you know the molecular formula mass is 180.2, so you're just taking the molecular weight, dividing it by the empirical formula weight, and we get that this would be equal to 6. So there's 6 empirical formula units in the molecular formula. So we have C6H12O6. So that's the idea, it's just using the empirical formula from percent composition data. We can use that along with the molecular weight to give us the molecular formula. Okay, so let's talk about, like we had alluded that there's another way we can do this type of experiment or an additional way we can have information given to us. That's through combustion analysis. So we can take a sample. The sample is going to contain CH, usually O, but it could actually be any third element. So it could be nitrogen or sulfur or some other element. The key is CH and then some third element. Usually you'll see oxygen, but what ends up happening is all the hydrogen in the sample, so imagine this contains CH and X, all the hydrogen gets converted to water, and then the mass of water is carefully calculated. And then all of the carbon in the sample is converted to CO2. So all of the carbon in the sample is converted to CO2, then we calculate the mass of CO2 very carefully. And if we start with a pure sample, if we know its mass, if we then know the mass of water being produced, the mass of CO2 being produced, we can figure out how much mass of hydrogen was originally in the sample, how much mass of carbon was originally in the sample. And then so the mass of oxygen or any other element can be determined by difference. So if we know the mass of carbon and hydrogen, we know the mass of the sample, we know the mass then of that third element. And we can calculate it by difference. And then by knowing what the third, we just have to know what the third element is. We can't just say CH and some unknown element. We have to define the element and know what it is maybe from the way we synthesize this pure substance. And so let's look at a simpler example, just a stoichiometry problem. This kind of gets ahead, but it's the next couple sections after the combustion analysis problem or stoichiometry. You've probably seen this topic in high school. But this combustion analysis topic really involves the idea of stoichiometry, the idea that you have some chemical reaction taking place, and then you have some yield of product that's 100%. So we produce as much of the products as possible. And this actually should be 6CO2. I don't know where the carbon went. But the C6H12O6 combusts with oxygen, reacts with O2 to form CO2 plus water. This is one of those one of the three reactions we started the chapter with, the combination, decomposition, and the combustion reaction. So we're getting CO2 and water here. And so we can solve this problem. It's actually a pretty easy problem to do. How many grams of water can be produced by the complete combustion of 1 gram of glucose? And so if we wanted to figure out the number of grams of water that can be produced in this reaction, I take 1 gram of the glucose. I'm going to need to use the mole, so I'm going to need to use the ratio that for every 1 mole of the glucose that reacts, we get 6 moles of water. So because the reacting units and the coefficients here correspond to the moles or the molecules in the reaction, we need to convert the grams to moles. We've used the molar mass a couple times. It's 180.3 grams per mole. And then I can use the conversion for every 1 mole of the C6H12O6 that reacts, we produce 6 moles of water. And so this is just using this coefficient here. For every 1 mole of glucose that reacts, we produce 6 moles of water. And then 1 mole of water, we don't really need the liquid, just 1 mole of water. What's its molar mass? Just 1.008 times 2 plus 16. So just from the periodic table, it's 18.02 grams. So if I take 1 gram divided by 180.3, that's about 0.00555 moles of glucose. Should produce 6 times that number of moles of water. So it'd be 0.0333 moles of water. And then multiplying by 18.02, I get 0.600, not moles, but grams of water. And let's look at how our units converted. We have grams converted to moles, moles converted to moles of water converted to grams of water. So grams to moles, and then moles to grams on the end of our product. So if we have 1 gram of glucose that reacts and completely combusts, we would get the formation of 0.600 grams of water. And so then the question becomes, or the issue in the combustion analysis problem, is if we tell you how much water is produced by a reaction, you should be able to work back to how much hydrogen was in the sample or how much of the sample had originally combusted. So the combustion analysis problem is really a stoichiometry problem. So I think we just needed to see a stoichiometry problem. So we'll come back and look at some other examples of stoichiometry as we go. So the idea of stoichiometry is just from the chemical reaction, like for say 2H2 plus O2 goes to 2 water. Let me zoom in here a little bit. The idea here is that you have 2 molecules of hydrogen. You can picture this as 2 distinct molecules of H2 reacting with 1 molecule of O2, producing 2 molecules of water. So our coefficients are just relating to the number of molecules you have. Or you can think on the mole level. You can multiply molecules by Avogadro's number. And so the ratio of the molecules to moles is still 2 to 1 to 2 for 2 moles of hydrogen reacting with 1 mole of O2 to produce 2 moles of water. It's going to be harder to picture. Like we can't write an Avogadro's number. It might take a while to write 6 times 10 to the 23 and then double that for the other one. But the ratio is still the same. It's 2 to 1 producing 2. And so we can use the ratio that if this reaction is going to take place, for every 2 moles of hydrogen that reacts, 1 mole of oxygen has to react with it, then you get 2 moles of water produced through that reaction. So these things are going away as we're producing our product. So we're losing our reactants, gaining our products in the reaction. So the coefficients are telling us the relative number of molecules or moles. So moles, I think, are the more useful unit to think of when we're doing problems of stoichiometry, because usually when we do a stoichiometry problem, we're doing it with a large mass. It's going to be easier to picture mole ratios than counting and picturing distinct molecules, because the molecule count would be way too big. But then the ratios are the same. So the ratio of molecules and moles are the same. If we have a molecular picture, we can picture that at the molecular level. And so let's look at an example of a combustion analysis problem here. So we're told that hexanoic acid, interestingly, I guess that's the compound that makes socks smell, is comprised of CH and O. And so we know that we're combusting a 0.225 gram sample of the compound. So we have a pure sample of this compound, 0.225 grams of it. And then it produces, upon that complete combustion reaction, 0.512 grams of CO2 and 0.209 grams of water. What's the empirical formula of the compound? Just like our percent composition, we're going to see that this information is giving us the mass information. It's giving us ratio on the ratio of the mass of C to H to O in this compound. So the best we're going to be able to do is still that empirical formula. So we still can't directly get a molecular formula from this information. We still can only just get that empirical simplest ratio formula. Now let's take a look at how it is that we might go about this problem. The way I like to approach it is we can figure out the grams of carbon that we produce from the CO2. Then we can figure out the number of grams of the sample of hydrogen from the water that's produced. So we can look at the mass of water to get the mass of hydrogen that had to be originally in the sample. And then we can get the mass of oxygen by difference, by taking the sample minus the grams of carbon minus the grams of hydrogen. So we're getting the grams of oxygen just by simple difference of what we know the sample of all 3 elements contains, and then subtracting off the other 2 elements' masses. So how do we get the mass of carbon and CO2? If I had told you that you have 0.512 grams of CO2, could you tell me how many grams that sample contains of carbon and how much of the mass of that sample is the oxygen? It's a pretty easy problem, right? It's just a few different ways of calculating this might be taking the 0.512 grams of CO2, and you're really just multiplying this by the percent C by mass of CO2. Remember the percent mass, the percent by mass would just be like 1 times 12.01 divided by the formula weight. And so what this would look like here would be if I took the mass of carbon, could be AMU, grams will make more sense since we're in grams, so we have this many grams of carbon that are present in ratio with the formula weight of the compound. So the formula weight of CO2, or the molar mass, would be 12.01 plus 16.00 times 2. That's 44.01 grams per mole. You see how that's just the percent carbon. It's the mass of the carbon divided by the formula weight of CO2. So this is just the percent or the fraction of carbon in the sample. So that's just the percent C in CO2. So we can multiply that out. I get 0.140 grams of carbon. We can do the same for the mass of hydrogen and water. What's the percent mass of hydrogen and water? You'd have 2 times, because you have 2 hydrogens, 2 times 1.008, that's 2.016 grams of hydrogen that are present in the sample for every 18.02 grams of water. So here we're just thinking the percent H in water would be 2.016. Let me actually write this slightly differently. Let me write that as 2 times 1.008 divided by 18.02 is the percent hydrogen. So we have 2 hydrogens in water. So 0.209 grams of water times 2.016 grams for every 18.02 grams. That gives me 0.0234 grams of hydrogen in the sample. And then the oxygen mass, do you see, we know the carbon mass, we know the hydrogen mass, we know the total sample was 0.225 grams. So if I take 0.225 minus 0.140 minus 0.0234, I get 0.0616. So 0.0616 grams of oxygen. So now these are the ratios of the masses of these atoms in the compound. Just like the percent composition problem, I can just convert these into ratios of moles. I could calculate mass percentages, I just don't have to. Like I could say, what's the percent C in the sample, what's the percent H, what's the percent O by mass. We could take like 0.140 divide by 0.225. We could take the percent of hydrogen. We could calculate percentages and do the problem exactly the way we did previously, but we could also just convert these to moles. I could go 12.01 grams per mole of carbon, 1.008 grams per mole of hydrogen. Clean that up, 1.008 grams per mole. And then oxygen, 16.00 grams per mole of oxygen. And I can work those ratios out. So I get 0.0117 moles of hydrogen, moles of carbon. .0234 divided by 1.008 for moles of hydrogen. That's 0.0232 moles of hydrogen. .0616 divided by 16 is 0.00385. What is that noise? This side of the room probably hears it. This side of the room probably doesn't, but it's a weird beeping sound. Okay, so which of these is the smallest moles? It's the oxygen. If I call that X, I'm going to divide all these by X. So we're going to divide them all by the smallest number. I get 3.03 for carbon. 0.0232 divided by 0.00385. I get 6.03. And then to 1 mole of oxygen. And so those are close enough to round to C3H6O. Because we're within about 0.03. It was what we wanted to be within approximately to be able to round. Now occasionally we won't be able to round. If we don't have whole numbers here, we're looking for a multiple. We're doubling, we're tripling, we're quadrupling. So if you ended up with one of these numbers is like 5.5, we'd have to double. If one of these is like 3.33, we'd have to triple. So we're just trying to find a multiple, but the best multiple is 1. And then we just be going empirical formula weight divided by the molecular weight. We'll look at that second problem at the start of class on Friday. All right, guys, that's it for today. Thanks for attending. I'll see you later.